These are the answers to the notes for the new unit on kinetics. First thing we're going to do is define the term reaction rate, which is defined as the speed at which a chemical reaction occurs. Now we're going to talk about reaction mechanism, which is a step-by-step molecular level view of the specific pathway. How do we get from reactants to products? Now, there are four factors that cause reaction rate to change. Those are the physical state of the reactants, the concentrations of the reactants, the temperature of the reaction, and the presence or lack of presence of a catalyst. Question B asks us to explain why 10 grams of powdered zinc will react with hydrochloric acid more quickly than a solid zinc strip that weighs the same mass of 10 grams. Well, the reason is that the powdered zinc has a much larger surface area. These are just specific locations where the reaction can occur. So there are more collisions per unit time, which means that there's a faster rate. A few more questions describing these factors that affect the rate. Part C, explain why the sample of magnesium metal will react more quickly in 10 molar hydrochloric than it will in 1 molar. Well, the more reactants you have physically present, then the more reactions that occur per unit time, which means a faster rate. Part D, explain why an Alka-Seltzer tablet will dissolve more quickly in water at 80 degrees C than in water at 20 degrees C. This is because at the higher temperature, the particles have a higher kinetic energy, which means they're moving faster. And if they're moving faster, they're going to collide more frequently. And if they do that, the reaction rate goes up. Part E, we want to describe the role of a catalyst. Well, a catalyst speeds up a chemical reaction, but it does not itself become consumed in the reaction. We're going to come back to visit this at the end of these units, the end of this unit on kinetics. Part F is the frequency of collisions between reactant molecules increases. How will the rate of the reaction be affected? Well, the more frequent the collisions occur, of course, the faster the reaction occurs. All right, now this next little subsection on reaction rates. The units that we use to measure the rate of a chemical reaction is molarity per second, molarity per minute. It's really molarity per unit time. The most common units of time will be seconds and minutes, but it is certainly possible to put this in terms of hours or days. Part B, in order to determine the reaction rate, the concentration of the reactant or the product is measured over time to see how fast it changes. Now we've got a little picture here off to the right showing how A converts into B. Now for part C, we've got a table below and it's based on a chemical reaction, very simple reaction. A goes to B. And we want to fill in the missing values for the amount of B produced. And we can see here, as I go through time in seconds, we can see the concentration of A goes down. But because the stoichiometry is 1-to-1, that means, for example, after 10 seconds, I only have 0.73 moles of A in the flask, but that means I have 0.27 moles of B, because it took 0.27 moles of A to turn into B. Likewise, we can do the same for the other points in the concentration profile and get a graph of the moles of A and the moles of B per time. All right, so now the next part, in fact, asks us to do that, to create the graph from the table. So we've got a little graph here in your notes. You need to stop the video and you need to actually go fill in the points on the graph. There's not that many. It will take you maybe 30 seconds to do the whole thing. We want to do two lines, one for A and one for B. So one for products, or A would be the reactants, and one for B, the products. And when we do that, we're going to do a solid line for A and a dashed line for B. When we graph it, we get this. just a nice, interesting line. These lines are mirror images of each other, which is not a surprise because it's just 1A goes to 1B. All right, now, how is the average rate of a reaction calculated for a particular time interval? Well, what we're going to do is we're going to compute the change in the concentration of B divided by the change in the time. And really what we're computing here is the slope of this line at any moment in time. So we're going to take our delta B, or divided by delta T, or in the case of the disappearance of A, it'd be delta A over delta T. Now, based on the data table from part C, we're going to calculate the average rate of disappearance of A for each of the following time intervals, and our units should be molarity per second. Now, if we do that, we can compute these times, and we fill in these times just by looking at the differences. And this is not the little chart here on the lower left-hand corner. This is from the actual data we were previously looking at. And you can see that as we go in each of these 10-second intervals, the disappearance rate gets smaller and smaller. And this makes sense, right? We're running out of reactants. So if we're running out of reactants, the concentration in the container drops. And if the concentration drops, the rate drops. All right? So we want to examine the values for average rates that we calculated in part F. How are they changing over time? Are they increasing, decreasing, or staying constant? You can clearly see that these are decreasing. All right? Now, H, why is it typical for reaction rates to decrease? Well, we've just discussed this. It's because the concentration of the reactants is decreasing, and that causes the rate to go down. We're going to define the term instantaneous rate, and that's the reaction rate at any particular instant. Now, in high school, we are going to stay with algebra. When you do this in college, you will use calculus to do this. So rather than delta molarity divided by delta time, it'll be dm, or in our case for concentration of A, it'd be dA dt. So the instantaneous rate at time t equals 0 is called the initial rate of the reaction. This is going to be very important as we try to compute some numbers later on down the road here in a few minutes. Part K, suppose that in a certain reaction, the change in A divided by the change in time is twice the change of B with respect to time. Which of the following reactions is consistent with this rate information? Well, you can see that that would be the first one, 2A plus B goes to C. And the reason is that the change in A is twice the change in B for the same time interval, so we need a reaction where we get 2 moles of A consumed for 1 mole of B. All right, now we have another reaction here. 2HI decomposes to hydrogen and iodine, and at a certain moment in time, the rate of formation of H2 is equal to 1.8 times 10 to the minus 6 molarity per second. Calculate the rate of disappearance of HI at this moment in time. Well, it's pretty easy to see if we have a balanced reaction that the rate of change of HI is going to be twice the formation rate of H2, and it's going to be negative because although H2 concentration is going up, the hydrogen iodide concentration is going down as it reacts, so it'll be negative. So we're going to take our number from part L and multiply that by minus 2, and we get negative 3.6 times 10 to the minus 6 molarity per second. All right, part M. The graph to the right, and originally in my notes it was on the right, now it's below here, displays the change in concentration for each species in the following reaction. We want to label each curve on the graph as A, B, or C, and here's our reaction. 2A decomposes to form 2B plus C. So when we look at that, we can see we've only got one reactant. That will be A, and that's the one that must start high and go low. Now the other two are our products. And you can see that the top one is going to be B because it's going to be twice as much at the end of the reaction as component C. So sometimes it's easy to look at the graph and see what's happening, but you kind of have to get comfortable with looking at the graph. All right, now we're going to talk about, in the next section, concentration and rate laws. All right, below us here we've got 6 experiments that we've run where we've reacted ammonium and nitrite. So the independent variable is the concentration of ammonium, and the dependent variable is the observed initial rate of reaction. Concentration of nitrite ion is held constant. What is the relationship between these variables? Well, we want to compare run 1 to run 2. And the reason we want to do that is because if you look at it, you can see that in comparing these 2 runs, that the nitrite concentration stays the same. But what we do notice also is that the ammonium ion is starting out at 2 different levels. Because it's starting out at 2 different levels, we get 2 different rates. So we can look at this and we can see what is the relationship between the independent variable and the dependent variable in experiments 1 and 3. Well, if we look at 1 and 3, we see that the ammonium concentration is doubled from 0.01 to 0.04, or not doubled, quadrupled, from 0.01 to 0.04. And if I look at the rate, 5.4 times 10 to the minus 7th times 4 would be 21.5 times 10 to the minus 7th. So the concentration is quadrupled and the rate is quadrupled. All right, now question C says in experiments 4 through 6, the independent variable is the concentration of nitrite, and the dependent variable is the observed rate of the reaction, and the concentration of ammonium is held constant. So now, instead of looking at these other reactions, now we're going to look at 4 and 5. Because if we look at 4 and 5, we see that the ammonium concentration is constant, but what's changed is the nitrite concentration. You can see that nitrite has doubled. And now if I look at the observed rate at the beginning, the rate also doubles. So we can say, well, the concentration is doubled and the rate is doubled. Part D says, what's the relationship between the independent variable and the dependent variable in, pardon me, experiments 4 and 6? Well, if I look at 4 and 6, I can see that ammonium is held constant. Nitrite has quadrupled, as has the observed initial rate. So the concentration is quadrupled, rate is quadrupled. All right, now we're going to define the term rate law, and we're going to give an example of a rate law by using the following equation. The rate is equal to K times the ammonium concentration times the nitrite concentration. So a rate law is an equation which shows exactly, mathematically, how the rate depends on the concentration of the particular reactants. And here, the rate is directly proportional to both ammonium and nitrite. Now, the rate law generally has the form rate is equal to K times that one reactant raised to some power m and the other reactant raised to some power n. And we want to talk about what these terms mean. K is the rate constant, which depends on temperature. M and n are small whole numbers called reaction orders. And we want to use this data to compute K. Well, we can pull any piece of data off the table. We know the rate because it's on the table. We don't know K, but we do know the 2 concentrations for ammonia and nitrite. We plug them in and we get our value, 2.7 times 10 to the minus 4th meter second, both to the minus 1. And I'm going to stop there and we'll pick it up in the next video.